Hey, welcome back. This expression's not too interesting. As k and x go up, the value goes up. And if we want to know if it equals 17, say, we just have to check some small values of k and x. But this expression is super interesting. Books have been written about it. So why is that? I mean, as k goes up, the value goes up, and as x goes up, the value goes down. But that means maybe there's some huge values of k and x where this expression equals 17, say. That's kind of a mystery. And also, we really care about this expression because members of 3n+1 loops take the form blah 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 over 2 to the k minus 3 to the x. So just for instance, if this ever equals 1 for some huge k and x, then these members of these loops are integers, and we've got some huge counterexample to the 3n+1 conjecture. So what kind of a thing is 2 to the k minus 3 to the x? I mean, what kinds of numbers can or can't take that form? Well, first, it's not even because it's a even minus an odd. It's also not 3even, divisible by 3. And it turns out, actually, it can never equal 1, except for the trivial case of 2 squared minus 3 to the first. And that's actually kind of hard to prove directly. I mean, who's to say there's not some huge k and x where 2 to the k and 3 to the x are adjacent? But if we take an apparently harder version of the question, it's easy to show that 2 to the k minus 3 to the x is never 1 mod 8. That is, it's not 1 or 9 or 17 or 25 or any number of the form 8n+1. Are there other restrictions on it? Like maybe it can't be 7 mod 12 or 17 mod 91. And the answer to that question is pretty bizarre, and we'll look at it in the next episode. For this episode, let's ask the general question of how many numbers between 1 and n can be represented this way as a function of n. This is sort of like when people ask how many primes are there between 1 and n in general. And just like with primes, the values of this expression here for small k and x already look pretty random. Here's k on the vertical axis and x on the horizontal. So 2 to the fourth minus 3 squared is 16 minus 9, or 7. Okay, so let's ask how many of these values are less than 32 in this whole chart. Well, 2 to the fifth minus anything is going to be less than 32, so we'll need to include the next row no matter what's on it. Okay, so far we have 1, 2, 3, 4, 5, 6, 7 values less than 32. And when we build the next row, let's notice that everything's bigger than the number below it because we're incrementing k without touching x. Okay, and we've got 37 here, which is bigger than 32. So maybe everything on up this chart is going to be bigger than 32. Should we stop? Nah, let's keep going. Okay, so far just getting bigger. But here at k equals 8, x equals 5, we have 256 minus 243 equals 13. And that's our 8th value in the chart that's less than 32. But, obviously it's hard to know if we're done. I mean, maybe if we keep going way up, we'll find 17 or 31 or even 13 again. And maybe 13 will just keep showing up over and over. Well, a couple of Dutch mathematicians took care of that last part. So see the 2 5s and the 2 13s here? They proved that those are the only repetitions ever in this chart. But still, maybe a number like 17 or 31 is going to show up at some point. Maybe we'll see every number less than 32. Well, not every number. We already ruled out a bunch. But the question still stands, and our general question certainly still stands. So let's look at some data. First, we're looking at this triangle of values because over here, x is too big, and 2 to the k minus 3 to the x is negative. So those values don't bear on our question. And second, this edge here is super jagged and unpredictable because the slope is log 3. So that's the usual crazy, jumpy stuff. Okay, let's look at this red line here. It shows all the values less than 2 to the 50th. That's because k equals 50 here, and 2 to the k minus anything is less than 2 to the k. But just like our 13 before, there's one more kx pair here sitting like Newfoundland off the coast of Canada, where 2 to the k minus 3 to the x is also less than 2 to the 50th. And another famous Newfoundland is up here, which is surprisingly low, a near collision in astronomical terms. All right, we've got to include them in our accounts. And the problem is they're super unpredictable. Okay, so let's say our n here is 2 to the 50th. All of the values in this red triangle are definitely less than 2 to the 50th, so we start with them. And now our problem is to add in these Newfoundlands. Here's where the heavy artillery of Baker and Ellison comes in. They showed that 2 to the k minus 3 to the x grows fast, faster than 1.8 to the k. And if we pick k equals 60, for instance, we have 1.8 to the 60th, which is about 2 to the 50th. And that inequality here means that everything above this line is definitely greater than 2 to the 50th. So anything red is going to be under that line, which means we can upper bound the amount of red by calculating the number of cells in this big triangle, which is half of this big rectangle. And if we measure the height, we can see that if n is 2 to the 50th, log n is 50, so it's going to be a bit more than log n. And here's what it looks like in general. The height is log n over log 1.8, and the width is the same thing over log 3. And if we approximate all these constants, we get about 0.43 times log n squared. That means there are at most log n squared values of 2 to the k minus 3 to the x between 1 and n. And that's not too many. If you were running for office and got log n % of the vote, well, if there were 8 voters, you get 3. If there were 1,000 voters, you get 10. If there were 1,000,000 voters, you get 20. And if there were 1,000,000,000,000 voters, you get 40. Wait, you say you're actually getting log n squared votes. Okay, so you get 1,600 votes out of 1,000,000,000. A mathematician would say that you're getting almost no votes. Okay, I think we can improve the constant by ruling out this big white sub-rectangle here, but we're still at log n squared, which is not too many. Okay, see you next time.